Hi, this is David. Welcome to Part 1, Topic 1, Elton, Chapters 5, 13, and 14, which are primarily concerned with the capital asset pricing model. There is a single associated workbook for those that happen to be using learning spreadsheets. That workbook is T1.2, Elton, CAPM, that's short for Capital Asset Pricing Model. Sometimes we just call that the CAPM model. And then in that workbook, there are 4 worksheets. We have Chapter 2 for Chapter 5, 2 for Chapter 13. In terms of exam relevance, the green high indicates highly relevant, and then the orange is medium relevant. So we've got portfolio possibilities curve, the market portfolio, and then the capital market line and the securities market line, which really implements the capital asset pricing model. So 4 worksheets in one workbook. And we start with Chapter 5, Elton, on delineating efficient portfolios. And so here's a really basic application. We start with the expected return. So this would also be the first moment of the distribution, or the weighted average, if you will. And the expected return here in Elton's notation is just a weighted average of the component assets. So as we often do in finance, we start with the basic 2-asset portfolio. Pretty much everything we do here can be extended to n assets, and then we just flip over into matrix notation. But we start with 2 assets, very typical. And then the fraction of the portfolio is multiplied by the expected return of each of the components, gives us the expected return. So for example, if we have a 2-asset portfolio, it's a mix of 40% A and 60% B, where B has the higher return of 16% versus 10. And then so this portfolio here gives us everything we need to know to compute the expected return. It's just a weighted average of the 2 components. A weighted average of the 10 and 16 gives us a number that's in between the 10 and 16. Sometimes it's helpful to do things just like eyeball check. It's not a robust check, but just want to see that, well, in this case here, we've got a mix of long assets. We should end up with a number that's in between 10 and 16 as we do. Okay, then the second moment is the variance or the volatility. So volatility here is going to tend to mean annualized standard deviation. So volatility, for our purposes, really is a synonym with standard deviation. And here we've got the formula for the volatility of a 2-asset portfolio. This is the sort of thing you need to memorize. If you're studying carefully enough for the FRM, by the time you get to the exam, you will have done it enough that you won't need to memorize it really. It's so familiar. You can absolutely expect to be tested on this. Notice we've got here an outer brackets that takes a square root. That's because everything inside the brackets here is the portfolio variance. So if we remove that, we could also just as easily be calculating for the portfolio variance. We take that final variance and the outer brackets takes a square root there and gives us the portfolio volatility. But now the volatility is a little trickier here, right? Because we've got the portion of the asset squared times the variance of A, then the remaining portion squared times the variance of B, and then we've got this term that really accounts for the diversification. 2 times the weight of A times the weight of B, which again, that weight of B is 1 minus x of A, times here, multiplied here by the covariance between A and B. And the covariance between A and B, we absolutely need to know, is equivalent to the correlation, denoted here by Greek rho, multiplied by the 2 volatilities, right? So we've got sigma subscript AB, that connotes the covariance between A and B, and it's going to be equal to the product of the correlation coefficient between A and B, that's rho sub A sub AB, multiplied by here standard deviation of A, standard deviation of B. Okay, so that's just a way to re-express here by doing that substitution, the same formula here. We want to be comfortable with applying either of those. And so, for example, if our 2-asset portfolio has 30% weighted in A, 70% weight in B, and then B is going to have the higher volatility of 20%. Then here we've got an assumption for the correlation coefficient. You'll notice I don't have a percentage on that. This correlation is unitless. It extends from positive 1.0, which is perfectly correlated, to 0, which is uncorrelated, to negative 1.0, which is perfectly negatively correlated. So here we've got some pretty significant positive correlation here. That means the covariance between A and B, you should know, is going to be the product of 10% times 20% times the correlation coefficient of 0.3. Gives us here a covariance, and it's not unusual that this is a pretty low number, this covariance, given the units that it's in. And so the portfolio standard deviation is first everything inside the brackets before that square root. That's a useful number too. That's going to be the portfolio variance, right? So that's in the brackets. Here we've got the weight of A, which is 30% squared, times the, what's this here? It's the variance of A, it's really the variance of the returns of A. That's here, again, the standard deviation of 10% squared. So we do that again with B, right? The weight, 70% squared, multiplied by the variance, which is that 20% squared. So we get the A in, we get a term in for the B, and we don't want to forget the term that really handles the diversification benefits, or really incorporates that correlation coefficient. 2 times the weight of A times the weight of B times the covariance between A and B. So in that brackets, we're going to get a portfolio variance, which we then take the square root of that to get the portfolio standard deviation or volatility. And so we have an aim. How does covariance and correlation affect the expected return and volatility of a portfolio of risky assets? You'll notice this here is a reference to that spreadsheet T1.2.5, Elton portfolio possibilities curve. And so here's the portfolio possibilities curve. And we've got some assumptions here, risk-free rate, the two assets, and we see that imperfect correlation here is going to be represented by 0. So that's that row assumption. Anything less than 1 is going to be imperfect correlation. So realistically, everything's going to be imperfect correlation. And imperfect correlation is going to give it the curvature here, which above here in the upper region is concavity. Right? It's concavity because if we draw a secant line, which connects a point to a point here above, we're going to get a line that's below the curve, right? As opposed to down here, it's going to be above the curve. So up here, we say this is technically concave, but the other point about it is just simply that it's curvy and not linear anymore. In order to be linear, it would have to have perfect correlation, which we're never going to have. Imperfect correlation is the free lunch of diversification that gives us here a benefit, higher return for certain levels of standard deviation. So that now all I've done here is change that graph and illustrated here various assumptions for the correlation coefficient, or rho, ranging from perfectly negative in green to perfectly correlated 1.0 in red. So again, these lines are just a mix of the assets. So notice the red's the only one straight. That's perfectly correlated A and B. So it runs, notice down here, from an expected return of 4% and standard deviation of 10%. That's where we've got the whole 100% of the portfolio is in asset B. It goes in a perfectly straight line under the assumption of perfect correlation. It's a linear mix here up to this point here, which represents 100% into asset A. So only when there is perfect correlation do we have this straight line connecting a portfolio entirely invested in asset B and a portfolio entirely invested in asset A. As soon as we move here up horizontally, vertically here, we're lessening the correlation. We're into imperfect correlation in all of this. Notice the curvature here, the concavity here of this line changes. And it's that concavity that's really sort of illustrating the benefits of diversification, which is the closest thing to a free lunch that we're going to witness in finance. So imperfect correlation reduces portfolio variance is the point. The shape of the portfolio possibilities curve we'll see up here is concave, at least up here in the efficient region. That's because a straight line between any two points in the curve lies underneath the curve. Now that's not true. It's actually convex here in the lower region, but we tend not to think too much about this lower region. It's not efficient. Any of these, this point here is totally inferior, right, to if we go vertically up here to this point here, because this point up here, which is in the efficient region, has a higher expected return for the same exact level of standard deviation. So we would never prefer this blue point to this point here. However, notice the way that we can characterize, that Elton characterizes this portfolio possibilities curve. It is true that this is the set of minimum variance portfolios. Notice I didn't say global there. I just said minimum variance portfolios. All that means is conditional on a given return. So for example, it is true of this blue line, of blue dot. Although this blue dot is inferior really to its sort of neighbor up here to the north vertically, which has a superior return, it is true that given an expected return of 5%, this blue point is superior to anything over here to the right. It's the minimum variance conditional on a given return of 5%. So you see how, in other words, these points are to the furthest left given any expected return. And in that sense, Elton calls this portfolio possibilities curve the set of minimum variance portfolios. And I'd just like to remind that really means a set of minimum variance portfolios conditional on a given return. So then we have defined the minimum variance portfolio, which this aim really should say the global minimum variance portfolio, shouldn't it? Now that we know that we just looked at the line, which is the set of minimum variance portfolios. So I think a little bit of a typo there really should be the global minimum variance portfolio. So it's not the best portfolio. The best portfolio is probably somewhere up here where we're trading off some risk in order to gain more return. The global minimum variance portfolio is simply the portfolio here in the line with the lowest standard deviation. Okay, but we don't expect that to have a desirable return. In fact, from the perspective of a Sharpe ratio, we do not expect it to have the highest Sharpe ratio. So under a set of assumptions in the mean variance framework, we don't expect to select this portfolio. The only reason for selecting this portfolio is we absolutely just want the lowest possible standard deviation without regard to risk. We can solve for the minimum variance portfolio by taking the first partial derivative and setting that equal to 0. And so that gives us a solution here for the minimum variance portfolio. So a natural question here is, do we have to memorize a formula like this for the exam? Okay, so I'm going to say that for most candidates, right, who don't have, aren't really deeply experienced and highly quantitative, I would not spend the time on memorizing this minimum variance portfolio. That's just my recommendation based on the amount of formulas that you're going to encounter and the relative, the less relative testability of this. I just don't think it's worth the effort for a formula like this. It takes quite a bit of effort to memorize, and then we don't, its occurrence has been minimal in the exam, and so it's just a statement about relative to your other formulas. I think it just drops down in terms of memorization. If you're really preparing a lot, and you really have a lot of background expertise, of course, you can go to the trouble, create more safety in your preparations. But at this point in the exam, I don't think it's worth it. However, I do think the exercise of understanding why this is a first partial derivative and a local minimum that we're solving for is very useful. Understanding why we can solve for a global minimum is very useful. Okay, but so I've got a question here from our own set. This question is BT305.1. A two-asset portfolio contains a long position in commodity T with a volatility of 10% and a long position in stock S, which has a volatility of 30%, and the assets are uncorrelated. So that means the rho T between T and S is 0. And what is the weight of the portfolio which should be allocated to the commodity if the goal is a minimum variance portfolio, or really a global minimum variance portfolio? So you can pause, go ahead and apply that formula that we just looked at. And if you plug that in, I hope, to the formula we just looked at, I think you should get about a 90% allocation to the commodity T with the lower volatility. So we're not too surprised that most of it goes into the commodity T. Although it is interesting, isn't it, that our global minimum portfolio is not, notice, it's not 100% into vol T. It's understandable if you look at this question and go, well, I'm going to put it all in T because it's got 10% versus 30%. But that's, again, the free lunch of diversification. We have uncorrelated assets here. And so we're actually going to do a little bit better to put 10% into this high volatility stock and take advantage of this uncorrelation to produce a portfolio. Notice that implies the volatility of this 90% portfolio is going to be less than 10% of the commodity T. That's the thing that's really striking. I think superficially, if that's not intuitive, I wouldn't blame you. It's not intuitive to me. How can we actually get a portfolio that has a volatility here of less than 10%? By mixing in an asset that has a volatility of 30%. So the efficient frontier is a concave function in expected return standard deviation space that extends from the minimum variance portfolio, and now we want to say the global minimum variance portfolio, to the maximum return portfolio. Okay, so that looks pretty symbolic, but visually it's going to be pretty straightforward. And here we are. Here's the portfolio possibilities curve in green. Remember, that is the curve of lowest variance given conditional on a certain level of expected return. So this green we think sort of horizontally for any given expected return. We're all the way over to the left and we're getting this curvy function. This curvy function here is concave in the upper region, convex in the lower region. So the efficient frontier starts with a global minimum variance portfolio, which is a single point, and includes the concave region. Up here, it's efficient. The risk-free asset has not yet been introduced, so this efficient frontier is concave, isn't it? Now we introduce the risk-free asset. We're going to anchor it at 6%. So it's really sort of an anchor over here, and then how is it constructed? Well, we just think about anchoring here, and then a straight line now that runs tangent to the market portfolio here. That market portfolio in red, it's not going to be, you can see visually, it's not going to be the global minimum. What that market portfolio here is the portfolio here in the efficient frontier with the highest Sharpe ratio. So in theory there would be the most excess return per unit of risk as given by the standard deviation. And now, so you can see by anchoring with the risk-free rate, by introducing it, the efficient frontier is going to shift from concave to a straight linear line in blue. Anchored, we can define it with only 2 points, the risk-free rate and the market portfolio, such that this line then becomes tangent to what was previously the efficient frontier before we introduced the risk-free rate. That means the capital market line is now efficient. For example, if we pick a point here on the blue line and think vertically, it's going to have, for the same standard deviation, let's say 20%, you're going to want to be on the blue line more than the green line, because for the same 20%, you can eke out some extra expected return. So notice how the introduction of expected risk-free rate introduces us into a set of superior possibilities here, such that after we introduce the risk-free rate, the capital market line now becomes the efficient frontier. And then we also see that with short sales, in theory, portfolios exist that give infinite expected rates of return. And so visually, that's moving up the capital market line. You can see that in theory, there's no limit here to how high vertically we can go. Of course, we're incurring greater and greater standard deviation as we do that. But then just to illustrate how that might look, if we put everything here, under those previous assumptions, a two-asset portfolio, if we put 100% in asset B, then the portfolio return is going to be 16%. But what if we shorted asset A 20% and used those funds from shorting to purchase additional asset B, where we now have 120%. So notice 120% minus 20% is we still have 100% portfolio, but we've leveraged ourselves by shorting. So notice how shorting can create leverage. We've leveraged ourselves into additional asset B and a higher expected return. So chapter 13 is standard asset capital pricing model, and really there's sort of two things here. There's the formula and there's the set of assumptions. And so I will tell you that really what's really essential is the formula, and that's because we know that it's tested every time. It's a basic finance idea. We're always going to be tested on this idea of the expected return of here. The sub I sort of suggests a security or an asset, but it could be a portfolio. It's going to then be the risk-free return plus here the product of what we call the quantity of risk and the price of risk, beta. Notice that beta sub I suggests that there's a beta associated with that security, and that's its sensitivity to this factor here, which we call the price of risk. And that's the excess return of the market. Notice market's expected return minus that same risk-free rate. So we call this the price of risk, sometimes called the market risk premium or even the equity risk premium. And notice we could subtract the risk-free rate out of both sides. That would give us on the left-hand side an excess return or expected excess return. Then it would be just a product of the two. The beta here can also be, we can also substitute an alternative expression in for beta, but this is going to remain the most important formula here for the capital asset pricing model. And notice what it really suggests here, that expected return is a linear function of systematic risk. That's the key point. Expected return is a linear function of systemic risk. So this is really a single factor model. Yes, that's very simple to think that the expected return can only be a factor of this model. So it's very simple, it's controversial, it's debatable. And again, the second point is just if we subtracted risk-free rate from both sides, we would get in the left expected excess return then just becomes the product of the price and quantity of risk. I like to think about it that way because it's very simple. Expected excess return is the quantity of risk multiplied by the price of risk. And then the manifestation there of the capital asset pricing model is a security market line, and it's straight also. So remember I said there are two parts to this really. The first is that formula that we absolutely need to know because we'll be tested on. And then sort of the qualitative piece is all of the assumptions that underline the capital asset pricing model. And if it's the first time you've seen it, there's probably more than you would have expected. And so this capital asset pricing model really is weighted down with a lot of assumptions. And you can sort of see why it's so debatable. If I were going to either take a position, if I wanted to argue, like say in a debate between argue for and support of the capital asset pricing or against it, I think it'd be much easier to argue against it because look at all of these limiting assumptions, these stringent assumptions that are required. And each of them has got its own sort of discussion, and many of these have been researched for years and years, much extensive research conducted against them. Okay, but then itemizing them, we've got no transaction costs. So this is the idea there's no friction. If we introduced transaction costs, that would complicate the model, although it doesn't really deal at a death knell of any sort. The assets are infinitely divisible. There's an absence of personal income tax. So there's a non-standard capital asset pricing that will later then introduce that assumption back in. Perfect competition. What does that mean? That means that as an individual, by your purchase or sale of your stock can't influence the price of it. The mean variance framework is really important to the capital asset pricing model. Easy to gloss over this because these terms are sort of abstract. But that means that investors make decisions solely in terms of those first two moments. That's the meaning of the mean variance framework. It means that risk reward is characterized by only mean and variance, first and second. So that's expected value and standard deviations. So that's why consistently you'll see our input assumptions are the expected return and the standard deviation. That implicitly assumes a normal distribution because we don't have any other input assumptions there. So it turns out to be a limiting assumption. Unlimited short sales, we saw an example of how that can create leverage. Unlimited lending and borrowing, that lets us move up and down the capital market line. Homogeneity of expectations. Okay, this is a key assumption. I think this is the most significant one. That all investors are assumed, well, there's two parts to this. So there's a single period. All investors are assumed to define the relevant period in exactly the same manner. And then the one I think is most significant. All investors have the identical expectations with respect to the necessary inputs into the portfolio decision. That is to say, expected returns, the variance of returns, and the correlation matrix, or the pairwise correlation set. So that means when we describe a set of assets and sort of put it here into this capital asset pricing model, we're assuming that if I'm an investor and you're an investor, we share the same views about expected return and variance. We get the same numbers. You can see that's I think highly unrealistic. It's highly essential. So to me, it's really arguably the most important assumption here. It's unrealistic, but it's one we make. All the assets are marketable. And then a key thing about the capital asset pricing, this is all assets, including human capital. So a lot of assets here that we don't typically include in a superficial look at the capital asset pricing model. And so the capital market line, which you've seen this before, is the set of optimal portfolios. It's a linear combination of the market portfolio in red here and the risk-free asset. So again, there's really two steps to getting there, right? That first step was construction here of the portfolio possibilities curve, the green line. The green line, which is concave and then convex, although efficiently it's just concave. The concave efficient frontier in green is a mix of different risky assets. It does not include the risky asset. So we mix the risky assets and we decide that because based on the Sharpe ratio, highest Sharpe ratio, there's a mix of risky assets that creates or that points to the market portfolio in red. That's a point on the green. Okay, so then under this capital asset pricing model, what we said is with all these assumptions, because investors have the same perspective, they're all going to decide that that's the optimal mix of risky assets. So that first step here is looking at the risky assets and decided the best set of risky assets is the market portfolio. Any other set of risky assets is inferior. So then the second step then presumes that's your risky decision. The second step is the capital market line, and it's only the two choices. It's an allocation between a risk-free asset and the market portfolio. We don't then go back and then decide there's a different mix of risky assets. That point has been that's often confusing, we know in the forum. But that capital market line is a simple asset allocation decision between risk-free and the market portfolio, which itself is the same set to everybody of risky assets. This is not an aim, but it has been. It's worth observing this, that the capital asset pricing model's assumption of perfect market requires, or really depends on the strong form of efficient market hypothesis. So there's a dependency here. If we're going to use, when we assert the CAPM, or when we really use it in a model, we're implicitly assuming strong form of efficient market hypothesis. That's why you will see sometimes academics make that sort of linkage because they know that there's a dependency there. Now let's take a look at Elton question 13.1. Assume the following assets are correctly priced according to the security market line. And let's derive the security market line. So we're given two assets with expected returns and then their betas. They each have different beta. That's their measure of, that's their sensitivity. So what must be the expected return on an asset with a beta of 2 given this information? Go ahead and hit pause and see if you can work that out. Okay, so hopefully you're able to notice that we have two unknowns here, but we also have an access to two equations. We're given the two assets. One of our assets has an expected return of 12% because its beta is higher, 1.5, than the other, which has a beta of 0.5 and 6%. That's two. You should be able, in the FRM Part 1, to be able to solve for a simple set of two equations and two unknowns like this, such that, notice we can, the easiest thing to do here is just subtract the second from the first. That'll drop out the risk-free rate and tell us that the market risk premium must be 6%. That tells us that the risk-free rate must be 3%. Now we've really got the security market line, don't we? Here's the implied security market line, because basically that question gave us 2 points on it. And we're able to infer then the security market line. That then will give us the expected return for any beta. And if it's a beta of 2, as in the question, we should get 15%. Chapter 14, finally, is just the non-standard form of the capital asset pricing models. The testability historically has been less here, okay? And just a reminder that we had all of those strict assumptions on the CAP-M. But then what we do with the non-standard form is basically there's a tour through those assumptions where we relax some of those. And in many cases, relaxing them is almost inconsequential. In other cases, it's just a bending of the CAP-M, so it needs to be adjusted. In other cases, it's arguably threatening to the model. So allowing short sales is a convenient assumption that simplifies the derivation of the math, but is not a necessary assumption. If short sales are disallowed, we get exactly the same capital asset pricing model result. And then it's interesting, the model basically survives if we want to liberate the riskless lending and borrowing. In other words, if we release that assumption and suddenly there is no riskless lending and borrowing, that was that idea in the capital market line that we could move up or down by borrowing at the risk-free rate or lending at the risk-free rate, do whatever we want in regard to the risk-free asset. If we suddenly don't have that, we just end up with a zero beta CAP-M, right? Where instead of the risk-free return here, we have the expected return on a zero beta portfolio. So it's really at the same point horizontally on that x-axis. It's just where the beta is 0, there's a corresponding expected return, and then that's what this value is. So although conceptually there's a little bit more involved, really, formula-wise, all we've done is substitute in here the zero beta portfolio for what would have been the risk-free asset. Personal taxes. So each investor gets to look at a different efficient frontier if there are personal taxes, but markets still clear, it has been shown, to a general equilibrium, albeit a more complicated general equilibrium. So we have a variation then that allows for personal taxes. Okay, so an interesting assumption about the capital asset pricing model is that it includes all marketable assets. And what if we introduce non-marketable assets like human capital, and then this creates an equilibrium return that can be higher or lower than under the standard form of the CAP-M. So that does introduce a challenge to the capital asset pricing model. Also, an extreme measurement challenge when you think about trying to measure something like human capital. Heterogeneous expectations. Now, if we now release the homogeneous expectations, which we'll call, I argued, is the most arguably the most important assumption, we now allow for heterogeneous expectations. Equilibrium can still be expressed, but now these returns, covariances, variances are complex weighting averages of the estimates held by different individuals. So you can see how in a system when we introduce individuals, that's going to be very complicated computation. We have non-risk taking, non-price taking behavior. I'm not going to dwell on that. And then we do have a consumption-oriented CAP-M. We can do a multivariate version of the CAPM, which includes inflation. And we have a multi-period version of the CAPM, which bears a strong resemblance to our arbitrage pricing theory. So what we've got then are multi-beta CAPM, and as sort of a version of multi-period. And if you think about it, this starts to become more realistic, right? That one of the key problems with that CAPM, as we've said, the expected return of security is just a function of its beta. So its sensitivity to the one factor, which was the market's excess return or the equity risk premium. And if you thought that's unrealistic, you wouldn't be alone. So we have a multi-beta concept, which then says, well, okay, now the excess return could be a linear combination of several sensitivities to various factors. For example, a sensitivity to inflation risk and that common inflation risk factor. And so we can add a lot of these on. And then from a math perspective, we're very similar at that point to arbitrage pricing theory, although we make a distinction between APT models and multi-beta CAPM. But in terms of the formula, it's going to be very similar in the sense that we can now think about the capital asset pricing model that we study as just the most popular example. It's really an instance of the multi-beta CAPM. In fact, we might be better to think about a multi-beta CAPM and then say, so a multi-beta CAPM really tells us that the excess return is a function of several sensitivities to various factors that we can define. And then we've got an example of that multi-beta CAPM that happens to be the single factor CAPM, where it's our beta with respect to the market's excess, equity risk premium. So the thought I would leave you there is just start to allow yourself to extend into a concept where we can have several betas and then several common factors. And that concludes a review of Elton chapters 5, 13, and 14. Thank you.